Good morning, everybody. Great to see everybody, and a warm welcome to the latest edition of our Make It OMRON webinar series. With me today is my colleague Dave Breckell. Dave, would you like to give a quick introduction of yourself?
Hi there, my name is Dave Breckell. I'm the Market Development Manager for OMRON in the UK. I've been with the business about 15 years. I've been in the industry for about 30. My background is control panels and maintenance, but I mainly now look after our sort of components and sensing business.
Fantastic. Great to see you today, Dave. So today we're going to really focus on the issue of condition-based monitoring, smart maintenance, and how we can help manufacturers to drastically reduce their unplanned downtime. We're going to go through, some of the issues that are presented by downtime within manufacturing, but more importantly, we're going to really lean on Dave's knowledge and expertise in the industry to start to try and share some strategies that you as manufacturers can use to start to prepare yourself to adopt new technology and really overcome these barriers. So, I mean, downtime is quite a broad topic, and at OMRON, we tend to separate it into two primary camps. So we have what we call planned downtime and unplanned downtime. Clearly, machinery in factories can't run all of the time. It's impossible for factories to be able to produce at 100% efficiency. Some of the primary examples of why that isn't the case is machines need components replacing periodically, particularly if it's heavy on mechanical components. We need to do things like putting additional oil and grease in there. All of this takes time, but it needs to be done when the machine's not running. Similarly, product changeovers, especially when we're looking in more flexible factories where quite a high mix of products is going through the line. We need to be able to change various different machine parameters. We might need different packaging materials, and we also need to streamline the workflows of getting existing work in progress to the line. Again, all of which takes time and needs to be done when the machine's not running. These are all things that we would classify as planned downtime. The big issues occur is when stoppages are a surprise. And these are things like unexpected machine breakdowns. For example, a motor bearing goes, so all of a sudden that motor stops working, but actually it's your main in-feed conveyor for your machine. Examples like that start to cause really big productivity issues for manufacturers, and those issues can vary by industry. The obvious knock-on effect that springs to mind is that of cost, and again, different industries have different cost impacts. If you look at something like FMCG, for example, you could be looking on average, data kind of suggests in the UK, it's around about 400 to 500 hours of unplanned downtime in an FMCG factory every year on average. And when you look at that costing somewhere between about 15 and 25,000 per stoppage in terms of lost productivity, that really quickly mounts up to a pretty significant amount of money. But to be perfectly honest with you, FMCG gets off a little bit lightly, because when you start to look at some of the other industries where the actual value of the products they're producing is quite significantly more expensive. So let's take cars, for example. The costs start to really spiral to a point where actually they're pretty terrifying. So again, looking at some of the research and the data that we've done, on average in the UK, we see each factory can often lose around 60 to 100 hours a month in terms of downtime in the worst case scenarios. But again, cost-wise, it's significantly higher, because if you're losing, say, 100 cars an hour going off a line, all of a sudden that's a very expensive issue. And similarly in pharmaceutical, where actually the impact is even greater because of the regulatory requirements of having to clean up once we've been in to do any maintenance. Those unplanned stoppages can often cost into the millions per hour. So it really is an issue that as an industry we've got to grab a hold of and address. So we believe that technology is a key enabler for that, and Dave is here to help us try to understand that. So Dave, I've kind of described there some of the potential financial impact. We didn't really touch so much on the brand impact, which I think is quite clear. But can you give us some examples of the most common causes of unplanned downtime in manufacturing?
Well, for production machinery, you can broadly classify into sort of three areas. One of the most common ones that we find is issues with rotating machinery. So, that's things that are driven by electric motors and servo drives. That can be caused by vibrations and misalignments with the load there. And it can be used on devices, such as gearboxes, fans, pumps, conveyors. These devices are typically running 24/7 continuously when the production is running. Another area we find a lot of unplanned downtime is caused by is components within the panel failing. It could be due to over voltage, it could be overheating in the control cabinet. And then you have issues with mechanical and static equipment. It could be a belt breaking, it could be a component wearing out, it could be a misalignment, a flange or a pump or liquid or anything being supplied into the process there as well.
No, great. Thank you very much. I'm sure many people in the audience can understand from first-hand experience some of those scenarios you've described there. A lot of them have been around for many, many years now. But what is it about the traditional maintenance strategies that have been employed that are no longer working in these situations?
Well, but traditionally all maintenance was reactive. So they waited until a machine, if we use a pump, for example, as an example, that they would wait till that pump failed, and then a maintenance engineer would take it out of production and repair it. That's very, very costly because A, you don't know when it's going to fail. B, you have to make sure you've got the spares on site. You need a trained, skilled electrician to then do the work there. So it's a large variable. When I was an apprentice, probably 25 years ago, 30 years ago nearly, we were moving more and more to preventative maintenance. And that's where you had a time-based strategy. So you basically look at that pump and you'd say, roughly 2.5 years time it's likely to fail. So we'll schedule in 2 years time a maintenance period where you'll take it out of production and do all the sort of tests and checks that we just described. That's a good strategy, but it doesn't take into account the usage of the pump itself. So, that it might have run for 10 hours, it might have run for 10,000 hours. So you can often find yourself doing maintenance when either it didn't need doing because the motor was actually in reasonably good condition, or by the time you've got to it, if it had a high duty cycle, there might have already been some damage done to it that could have been picked up before. Now we move more to what we call predictive maintenance. So that's where we're getting real-time data from the components itself. So not only can we tell when it's failed, but we can actually predict when it's going to fail, and we can pick up conditions at a far, far earlier stage. So quite often it's something we might be able to rectify before the motor is even damaged. And then the final stage of that is to move on to what we would call smart maintenance. And that's where it's more data driven. So rather than just looking at an individual component, we can draw the data in historically and look at multiple items on a machine and trend it over time.
Oh, fantastic. You mentioned motors there on quite a few occasions. It seems like that's quite a key component that we should be looking at. What are the different things about a motor that keep it running, and what should we be looking out for when we're looking at monitoring these different things?
Well, traditional sort of, when people say condition monitoring for motoring, they're normally looking at vibration and temperature. So, if there's a fault on the motor, it will, say there's an issue with the cooling, for example, or the load, it'll start to vibrate, it'll get noisy, it'll heat up. We can do that, certainly, and there's lots of solutions on the market that can. You'll either have a physical probe on the motor itself or a wireless sensor. But the issue with that, though, is that by the time it's got hot and it's vibrating, it may have already done some damage. It's at a relatively advanced stage. We use essentially current analysis technology. So we can clip a current transformer onto the motor cable and we can actually do waveform analysis. This lets us pick up faults far, far earlier, and it also lets us check a wider range of issues with the motor. So, we can detect, for example, if the bearings are starting to fail or if there's bearing scratch, but also we can detect misaligned loads and issues with anything that is driving. An example of that could be if you had a submerged pump, for example, and it was starting to cavitate, we can pick that up using the current analysis. In addition to that, when motors do break down over time, especially if they're getting old, one of the big checks is insulation resistance. So the insulation on the rotor and the stator start to break down. That would typically be tested by, again, taking the motor out of production, putting a mega across it, doing an insulation resistance check. We can do this remotely, and we can even do it while the motor's running. So again, we can automate that task. When you're looking at something like insulation resistance, that doesn't just apply to motors. So we have specialist units that will work for heater burnout. So when you've got a resistive heater, where you'll have in many processes, when it's brand new, you've got essentially no oxidation. So you'll have a low resistance, but this will build up over time. And we have field devices that can detect that as well. When we're looking at things in the panel, because we mentioned obviously that was the second area where products can overheat for various reasons and fail, we have a series of thermal cameras. And the thermal camera systems are particularly clever because rather than essentially just looking at the overall temperature in the panel, you can monitor each individual component with a specific range. So the temperature that might be okay for running a transformer might be much higher than the temperature that's suitable for using a solid state resistor or a PLC. Temperature is critically important to machinery uptime because typically a device will have a temperature range. It could be -10 to 40, -10 to 55. As a pretty good rule of thumb, for every 10 degrees that you run that component over that temperature, you'll roughly half its lifespan. So if you imagine you had a device with a 10-year lifespan and a 50 or 40 degree maximum temperature, if you ran that at 50, you'd probably get about 5 before something broke down, whether it's a capacitor or an issue. If you ran it at 60, it'd be about 2.5. By using a thermal camera, we can set individual limits for each component, but we can also measure the rate of change. So again, we can detect it before it reaches that temperature. We can even predict when it's going to happen. Other sort of technologies we can also use, if we're looking into field devices, we have IO Link built into all of our PNP sensors, so we can get real-time analytics from the sensor, not just setting it, but we can see if there's an issue with it, if it's dusty, if it's dirty, if it's blocked with a proximity switch, for example. You can see if the target's moving closer and closer to it to avoid mechanical damage. And it can even just be down to a simple component. We a power supply. We have a lot of power conditioning products where our SAVKX power supplies, we can get data on the current draw, the load, the temperature, its approximate lifespan. Because obviously if the power supply goes down, that can take out your panel as well.
Yeah, so it sounds like it's fair to say that this technology doesn't just apply to things like motors, pumps, and heaters. There's quite a wide variety of machine components that we can monitor and we can apply these kind of strategies to. What are the primary benefits that manufacturers can unlock from this technology?
Well, obviously, the earlier you detect a fault, the better. Not just for scheduling, as I say, predicting when the failure is going to take place, but you can then schedule your maintenance windows. You don't really want to be stopping the machine to repair the motor one day and then stopping the machine to look at another component, So having that kind of analytic information where you've probably got 3 months or 4 months till this component fails, or 2 months till there could be an issue where this one's really helpful. It also lets you order spares in advance. Some things could be on especially when you start talking about specialist motors and other things, they can be on quite a long lead time. Some of our machine builders will actually use that data as well to provide a spares package, so they can organise for a maintenance engineer to be available at a certain time. And it also lets you balance your machines and line use. So if you've got 3 lines and one of them has been used an awful lot and there's a bit of degradation on the motors, you can balance the load across the other 2 to keep them running longer until you hit that maintenance window.
That's really useful information, Dave. Thank you. So for those manufacturers that are in the audience and they're thinking, do you know what, actually this sounds quite interesting technology, but cool, I don't really even know where to get started. Can you give us some practical steps that manufacturers can take for adopting smart maintenance technology?
Yeah, certainly. The feedback I've had from a lot of companies over the years is it can be quite daunting. Often, people have pitched systems that might monitor 200 different variables on a machine, and you can get essentially a bit data blind. What do you do with all this information? A lot of the systems on the market as well are quite large in terms of how many data points and IP addresses that they want to feed out into a cloud-based system, which presents problems as well. So suddenly doing a little bit of condition monitoring becomes a large capex investment involving IT and various other departments. For us, all of our devices, whether it's motor monitors, the thermal cameras, the other devices, they all use edge computing. So essentially, all the monitoring and the algorithms are done locally in the device or the controller on your machine or on your production line. The big advantage of that, essentially, is we can start small and scale it up. So, I would recommend you start with, if we were talking about motors, 2 or 3 critical motors that are running 24/7, that are the most difficult to mechanically change or for spare parts. We can start with this. We can feed that information into existing systems like an MES or ERP system, but we have some simple software that we can give free of charge, which can monitor them. We just have a traffic light, for example. Now, I've got some customers that even just take an alarm output and wire it into tower light for a simple start. But we can scale that then up to a large system if you want to.
Okay, and I guess a lot of this technology is dependent on sensors, right? So, you know, I've seen temperature sensors online that are dirt cheap, and I've seen some that are really, really expensive, and it's quite often quite difficult to distinguish between the two. So, what is the importance of having high quality sensors in these scenarios?
Well, if you're looking at sensors in particular, you know, obviously, IO-Link is a critical part of that. You know, it's an open standard that's supported by all sensor manufacturers. You know, as I mentioned before, you can get real-time sensor data on it. You know, if you're using an IO-Link enabled sensor, for example, for maintenance, you can set it so that the controller can actually set the sensor. So your maintenance person on the night shift can just plug the sensor in, and the PLC will recognize it, send the switch point to an optical sensor, configure it, and away you go. The other thing is, I think with the quality sensing product, the environmental resistances tend to be higher. So, you know, the vast majority of our new optical sensors that we sell now are all IP69K. They're stainless steel. They're designed for washdown and high pressure environments for food and beverage. You know, we put things like oleophobic coatings and air blasts onto them. So if you're in a dusty, dirty environment, it keeps the lens clean, for example. So yeah, quite often buying a cheaper sensor can be counterproductive because it's cheaper to buy, but you might, you know, just having to swap that out one more time. If you factor in the machine downtime, the spares, you know, the time it takes the maintenance engineer, it easily negates any cost saving.
No, superb. That's really helpful. And I guess the final point on that is, obviously, when we're bringing in new maintenance strategies, we need our maintenance engineers to be adapting the way that they work. What's the importance of training here?
I think training is important. You know, obviously you've got to be able to interpret the data, but I think it's actually slightly different. The big advantage of using these technologies is actually the fact that in industry, you know, we're finding more and more there's a massive shortage of skilled maintenance engineers. So, you know, typically in a site where we might have gone to it 10 years ago, there might have been 5 engineers. There's now 2 or 3. So more and more, what we're finding is, you know, operators are having to get involved in some of the maintenance tasks. You know, being able to swap over a sensor. You know, so for us, there's a number of advantages of using these technologies, and for the end customer. For the end user, obviously, you know, we're simplifying a lot of maintenance tasks that would have involved a skilled maintenance engineer. So, you know, doing something like checking the insulation resistance on a motor can be done by a non-skilled person. It's all being done by the device. Secondly, obviously, it allows you to remotely check multiple machines across multiple sites, so you can do more with less. So somebody in the office can do the job of physically where you might have had 2 or 3 maintenance people at 2 or 3 sites going around there as well. But then finally, I think the other thing that's very important is that you have a user-friendly machine interface which you can provide, so that an operator or a semi-skilled person can actually interpret that data. As I mentioned, that could be as simple as an HMI screen or a remote screen you could have on a PC, giving you a traffic light. You can delve into further information, but it's making it user-friendly and easy to sort of interpret for the layman. Yeah,
I guess it's as you said earlier on, we can often take too much data, can't we? We've got to be able to convert those into insights, and I think that's really important. So I think it's fair to say, based on everything we've discussed so far, that really this is starting to rapidly become a non-negotiable for manufacturers, that they have to start adopting this kind of technology to remain competitive. But if we flip that on its head a little bit and actually look at new machines, how can those companies that are actually making machinery start to adapt their machines to fit in with this kind of methodology?
I think it's just about designing this in from the very beginning. You know, so at a very earlier stage, it's looking at, say, using a machine controller or a PLC that has advanced communications on it. You know, I mentioned things like IO-Link. Well, for that, obviously, you know, you need something with an IO-Link master to actually communicate with the sensors. A lot of our controllers now, they'll have OPC UA server, and they can actually write directly to database, because, you know, we can start small, but at some point you want to get that data and that information out into the field. You know, you can also pair that with remote connectivity. You know, so obviously there are a lot of solutions on the market. You know, we have ours as well, where you can have essentially a GSM or a 4G modem. It's not always easy to get an IP address. when you're designing a machine, you have to do battle with the IT departments, etc. So you can design that kind of technology in as well. And then there's other technologies you can put in at the design level. We have one called automation playback. And essentially what we're doing with automation playback is if there was a mechanical failure or something stopped the machine and it wasn't picked up by our condition monitoring, you can actually go back and it spools all the production data. So you can even put a webcam into it. So you could scroll back 3, 4, 5 hours, physically see what went wrong with the machine. You can analyze the data from, say, your motors, your servos, your PLC. It makes it much, much easier to then identify faults if you're, as a machine builder, you're trying to remotely diagnose and then send out maintenance engineers.
Yeah, great. So it sounds like that there are things that both manufacturers and machine builders can do. Now there are obviously some form of risks associated with this. The first one, I guess, is complexity. How complex is it actually to integrate this technology to existing systems?
Well, as I kind of mentioned before, because we use edge computing, so essentially, whether it's a motor monitor, it's done within the actual controller in the panel. A lot of our checks can be done within the PLC itself. If you're monitoring an IO link for the sensors, it's relatively easy to fit it on top. One of the concerns that I find with a lot of customers is, if you may have an older production line or a machine or a process, you might find that the PLC is 10, 15 years old. You don't have access to the source code. The last thing that people want to be doing is going in there and taking data and altering the logic in it and risking causing more problems. So, with our systems, as I mentioned, you can start small and scale it up, but also it's designed to sit on top of your existing control system. We can design one from scratch, but you can basically fit 2 or 3 motor monitors onto there. As I mentioned, you could just put it into a simple piece of free software we provide. You can put it into a tower light, or we can feed it into a cloud-based system or whatever MES or ERP system you have as well. So it's, it does sit on top. It's a completely separate system. We can integrate it, but I would start small, fit on top of your existing system, and then scale it up from there once you've seen appreciable benefits from what you're doing.
So it sounds like those risks in terms of complexity are relatively small, to be completely honest with you, Dave. Cost-wise, is this a big investment? Is it something we can do? You mentioned several times there about starting relatively small and scaling it upwards. Is that achievable from a cost perspective, or are we looking at significant capital investments here?
No, definitely not. Again, by starting small, if you were looking at motor monitoring, depends what you want to do, but if you're looking at, say, insulation resistance, we have products where, for a couple of thousand, you can monitor 7 or 8 motors at a time, something like the K7s. All of our standard products, like our sensing products, IO Link is built in as standard, so there's no cost to it at all. All you're doing is rather than having standard IO in the PLC, you have an IO Link master, which could be a slice on the machine, or it could be if you've already got your PLC and your control system, it's just a field-wired high IP sensor box on there. But you're right, by starting small, it becomes OPEX rather than CAPEX. So you can start small at your maintenance budget, make a couple of small changes, swap the power supply out for an intelligent unit. Our PLCs, again, as I mentioned, that they have these features built in as standard. So if you're looking at some of our OPC-UA PLCs, some of our low to mid-range PLCs have that built in with Ethernet IP, OPC-UA. So there's no great cost in terms of the hardware, but like I say, you can eventually scale that up to a very large system if you want to.
Fantastic. Final question, Dave. If it were you, where would you start?
Well, I would definitely start with motor monitoring and sensing. Those are the 2 quickest wins. Swapping into an IO Link sensor, we see a lot of failures with sensing, usually because of environmental reasons. Getting that data there. One of the big issues we have with sensing is obviously as well is that spares consolidation can be a big issue. People have to learn different sensors to program and set up. Using IO Link, that can all be done remotely from the PLC. You can plug it in, recognize it, send all the parameters to it. You can detect it before the actual line stops because it's no longer detecting products. And I would also start, as I mentioned before, with you pick 2 or 3 motors which are critical to your process, and then I would put on a current analysis system on there just to monitor them and make sure that the load and there aren't any issues with it.
Dave, my deepest thanks for sharing those insights. Some really, really valuable knowledge that you've been able to express there. So thank you very much. It really is an exciting time for manufacturing. Technology is evolving, and I think this is one that really has the potential to change our industry. As we start to look at different ways of doing business, different ways of managing risk. I think there is a clear role to play for both companies that are making and integrating machinery and those that are operating machinery. I think that dynamic will start to shift primarily because of this technology. When we start to look at remote diagnostics, being able to dial into machinery from a significant distance away. But we start to look at how things like machine learning and artificial intelligence are starting to come into mainstream industrial technology. We can then start to look at things like, can we actually adjust the speed of production on the fly to align with our maintenance data so that we're actually making it to the next planned downtime session rather than risking something that's unplanned. So there are loads and loads of exciting things that could start to come over time. So I'd like to thank everybody in the audience for joining us this morning. Today, we've really done a little bit of a deep dive into smart maintenance strategies and the benefits that it can have for manufacturers. Please follow us on LinkedIn and YouTube to learn more similar insights about this kind of technology and quite a large variety of others. And of course, you can reach out to either one of us directly on LinkedIn if you have any specific questions. So thank you very much, everybody, and enjoy the rest of your day.
Thanks, everyone.